In our last video, we were looking at least squares regression lines and using them to make predictions in a set of data where we maybe had some incomplete piece of data, and we would try to fill in the blanks using this least squares regression line. In this video, I want to take a look at something called the coefficient of determination, which is going to basically tell us how good that prediction is. So imagine we have two cases. Maybe we've got a picture. Let me do two of them here that looks like this. And then we've got another picture that looks like this. And then we've got our least squares regression lines for each of these. So maybe we've found the lines, and this is what the line for that one looks like, and this is what the line for the second one looks like. We can use these lines to make predictions. Again, the idea was maybe there's an x value. Oops, let me do that in a different color here. Maybe there's an x value where we don't know what the corresponding y value is, and we want to make a prediction. Right? We have all of these other data points, but we don't have one sitting at this particular x value. But if I go up to the least squares regression line at that x value, and then follow it over to where it hits the y-axis. So again, this would be the x-axis, this would be the y-axis, and this would be some x value of interest, something that we have. Then I can trace this back, and this would give me the predicted y value, which is going to be our y with a little hat over it. So this is some prediction. And we can do the same thing over here. Maybe there's an x value right here. It's our x value of interest. We've got our x and our y, and it will predict some corresponding y hat value that is our prediction. Okay, so we've done it in both cases. Which one of these two predictions is going to be a better prediction? Which one is going to be more reliable? So which prediction is better? Well, if you look at the data sets, this one over here has values that are further away from the line. So both of these two cases look fairly linear, but this one looks like it has a pretty strong positive correlation, and this correlation, also positive, looks a little bit weaker, right? These are very close to falling on the line, whereas these are a little bit more spread out. So this would have a higher correlation coefficient than this one. It also tells me that this is probably a better prediction over here on the right. Because the points are so close to the line's probably a pretty good prediction of the results of some new x value of interest that we don't have a y value for. Whereas over here, it could be on the line, but there's also a lot of points that are kind of far from the line. So we kind of have a little bit more wiggle room around this one that we might expect the y hat value to show up at. And so the prediction is not going to be as strong. So the answer is that the second one looks like a better prediction, a more solid prediction, because there's less variation between the line and where the points are. Over here, there's a lot more variation. A lot of the points are further from the line, and so I'm going to think that it's going to be a less reliable prediction. Still a decent prediction, but this one over here should be better. This idea highlights what we're going to be calling the coefficient of determination. The coefficient of determination is essentially going to be a value that tells us how good our prediction, how good we can expect the prediction to be. There's an appropriate way to put it. So this brings us to the idea of the coefficient of determination. The coefficient of determination is going to be a way of quantifying which of these two different graphs and these two different least squares regression lines is going to do a better job of predicting the outcome. And the gist of the idea behind it is the less spread out the points are, the closer they stick to the line, the better that line is going to be at making predictions. So if we take a look at a case down here, let me draw a picture of this. So let's look at another example real quickly. And let's say that we've got some points again. Let me just put a few of these on here. So here's our picture, and maybe here's our line. I want to do the same kind of thing that we did back when we divided this up into quadrants. So this is our x-axis and our y-axis, but I want to put a line right where y is equal to y hat. So basically right where the mean value of y is. And it looks like ballparking it, I'm going to say it's going to be right around here. So let me draw this in. Let me pick a new color here, and I'll draw this in as a dotted line. So this is just a totally horizontal line at the value y hat. This is the mean of the y values. If we look at all of these points, there's kind of basically two different values that we're interested in. And we can kind of explain how much this, so basically the goal is to come up with a way to explain how well does this line express the trend of the data. And we can break that into two components. So I'm going to take a look at this last point that we've got up here, just because it has kind of the most room to work with. This distance from here up to the line, and then this distance from the dot down to the line. Those are going to be the two different values I'm interested in. This difference right here is what we call the explained difference. And this smaller one up here, that tinier bit, is what we call the unexplained difference. So what do I mean by this? What is meant by these terms? The idea is that our line is meant to explain some difference. It's meant to predict a trend. If we just looked at the middle of the data and forgot about trying to follow any trend, but just said, oh, let's just pick the middle of the data, that would be this blue line right here. This is the middle y value in our data. Our line goes a step further and starts to explain the actual trend of the data and show that it's actually increasing. And so the line, the difference between this y hat value and the line itself, which is our, I'm screwing this notation up here. This should be y bar. I apologize for that. Y bar is what we always use for the mean of the y values. Y hat is the height right here at this particular point. So this is our y hat. Sorry for that mix up there. So if I look at the difference between y bar, which is just the middle of our data, and then this y hat, which is the part of the difference, the part of the trend that can be explained by the actual trend line, it turns out that is our explained difference of where this point falls from the line down here. So we can explain based on our trend line this much of the difference. But this little bit here is that part we were talking about up in these examples. How far does the line fall from the actual points? When those points are all close to the line, this distance, the unexplained difference that we've got here, is going to be really tiny. Whereas over here, when these points are further away, that unexplained difference is going to be a lot larger. And we want to make this unexplained difference as small as possible. Really, we want the ratio. So we want the following ratio. Of the explained difference over the unexplained difference to be as large as possible. Okay, so what I mean by that is I want our line to account for basically as much of the difference as possible. I don't want to have very big unexplained differences. So basically when I look at the explained difference, so the ratio that I just mentioned here can be written like this: the explained difference over the unexplained difference. I want that to be as large as possible. I want the top to be large and the bottom to be small, because this will make the overall number be a large number. So hopefully we get most of the difference to be explained difference, and we get very small amount of the difference to be an unexplained difference. And if we work that out, this turns out to be the thing that we actually call r squared, and it is our coefficient of determination. And it turns out mathematically, so the coefficient of determination, but it turns out mathematically that instead of having to actually find these ratios in the way that we're doing right here, this is related to the correlation coefficient. It is simply the square of the correlation coefficient. So we don't have to go through all this extra work of finding these explained and unexplained differences. So if you want to find the coefficient of determination, that's this right here, this r squared, all we really need to know is the correlation coefficient, and then we just square it. The calculator, if you're using the TI-84 calculator, it even spits this number out for us. But the whole point of it, the whole idea behind it, is it's going to be a measure of that tells us how well does our line actually approximate the trend of the data. How much of the trend line explains sort of the trend of the data versus how much of it is unexplained that falls off of the trend line. And the gist of it boils down to the picture we had here. If the points are more spread out, your coefficient of determination is going to wind up being smaller. There's more unexplained difference between the point and the lines. Whereas in a case like this, where the points are all very close to the line, there's very little unexplained difference. The line does a very good job of explaining the trend of the data. So hopefully that makes some sense. This section should be fairly short on the homework, and the way that you find this correlation, the coefficient of determination is simply to find the value of r, our correlation coefficient, and squaring it. And that's all you have to do.